In this video, I'm going to talk about the periodic trends that exist on the periodic table. Since we group the periodic table in order of increasing atomic number and by similar properties, other trends start to emerge on the table. So if you have a table in front of you, you can kind of analyze these things if you know what you're looking for. So we'll start to see some similarities here as you go across left to right across these rows, and as you go from top to bottom down these groups or down the columns. So that's what we're going to look at in this video. There are a few big trends we will look at, and there are some minor trends that'll emerge here. So it's all because the periodic table is grouped in this similar way here that these trends start to emerge. Before we totally get into the trends, I want to talk about the factors here or the things that influence these trends. So oftentimes when we look at these trends, we're going to, be asked, why does this happen? Well, it's going to come down to one of these three reasons on this slide. So we'll always reference back to this slide here as we're going through this video. So you have to definitely understand these factors and realize that even on the slides that when we're talking about this, I might give you a very detailed explanation about why a trend is happening, but it's always going to come back to one of these three things. So if you're trying to make this simpler in your head or as you're studying, remember it comes back to one of these three things. So the first thing is your electron energy level. How far you are from the nucleus is going to be an important factor here that might impact uh, these trends. So remember on the periodic table, we go from energy level 1 at the top, and then as you go down the rows, you go all the way up to energy level 7. So that's going to be important here. Something else called nuclear charge or effective nuclear charge influences these trends. Basically, the number of protons you have influences the pull on the electrons here. Nuclear charge is essentially talking about how strong your nucleus is. So if you have more protons in your nucleus, you have a stronger nuclear charge, if you will, especially if you're in the same row. If you're in the same row and you're getting more and more protons, your nuclear charge or the strength of your nucleus is just going to get greater and greater. So how many protons you have here influences the pull on these electrons. We call that nuclear charge or effective nuclear charge. It's really just talking about the strength of the nucleus and how strong it is at pulling in the outer electrons. And then the third factor here is called shielding effect. All right. This is the idea that the valence electrons, remember, the valence electrons are your outer electrons. So it's idea that these valence electrons are shielded by the pull of the nucleus by all the electrons in between the nucleus and the outer electrons. All right. So if you have more energy levels here with more electrons, you're going to have more shielding. The more energy levels you have, the more shielding that there will be. So if you want to look at this in a picture form, this Bohr model actually really does help explain this. So you can see here you have your nucleus in the center, you have your energy levels with your electrons, and you can see for this atom only has one valence electron or one outer electron. But the idea here is that you see how all these other electrons here in between the nucleus and the valence electron, see how they're there? They would feel the pull of the nucleus more than the outer electron because the outer electron is shielded from the pull of the nucleus by all of these guys. Remember, the nucleus is positive, the electrons are negative. There's kind of a pull taking place there. There's the opposites attracting. It's just that shielding effect says that these electrons feel the pull of the nucleus more because they're closer, and this guy on the outside doesn't feel it as much because he's shielded by the inner electrons. And obviously, if you had more energy levels here, you would start to even have more and more shielding, so the outer electrons would even feel the nucleus less and less. All right. So obviously these electrons that are really close to the nucleus here in the first energy level, they're going to feel the full pull of the nucleus. And then as you get to the second, they're not feeling it as much. The third, even less. And in this case, the fourth, it's even lower. All right, so the more energy levels you have, the more of this shielding that will take place. So ultimately, these factors are going to be the reason why these trends happen. So you always want to come back and reference these three things. The first of the big trends we're going to talk about here is called atomic radius. It's also known as atomic size. I will tell you, for all of these trends, the first thing you need to do is you need to know the definition. If you don't know what these trends mean, it gets very difficult to understand what's happening and why. So your first order of business here is knowing the definition for all of these trends that we're going to talk about, and then get into the understanding. All right, because you definitely need to think for these. These trends require thinking, and that's why a lot of times kids struggle with this. So the definition here of atomic radius, it's just like you would expect from kind of math class here. It's half the distance, okay, between the nuclei of two atoms of the same element if you put them side by side. So the idea here is if you took two atoms, like in this picture, of the same element and put them side by side, and you measured the distance between their nuclei, and you took half of that distance, that's why it's a radius, all right, you would have the atomic radius. The reason why we call this the atomic size as well, because think about it. If these atoms were very large and you put them side by side, and you measure the distance between their nuclei and you took half of that distance, it's going to be a larger distance. So that's why literally it is describing the size of the atom here. So that's the first thing you need to know is the definition here. But then there's a trend that exists with this on the periodic table, and you need to know this as well. So this would kind of be the second thing you need to know. So on your periodic table, as you go down any column, remember your groups here, as you go down top to bottom, the atomic radius or the atomic size is always going to get bigger. All right, so atoms get bigger as you go down. And we'll talk about why uh, in a second here. And as you go across any row, and by across we mean left to right. So you go across any row or period, the atoms are going to get smaller. So the size of the atoms get bigger as you go down the table, but then smaller as you go across left to right. All right. So this is not the why. This is just telling you what happens with the trend. If I ask you why, just saying, oh, because it gets bigger as it goes down, that's not the why. This is just explaining what is taking place here. So definitely know the definition and then definitely know the trend here. Now we need to analyze why this happens as you go down the group and across the row. So remember, it's always going to come back to one of those three factors we talked about before jumping into these trends. So for this one, as you go down, why does the size of the atom get bigger? Well, it makes sense. Every time you go from one energy level to the next, all right, you have more energy levels. So it makes sense that your atom is going to get bigger. It's going to take up more space. If you just look at this example, as you go down the first column on your periodic table, the alkali metals with hydrogen, as you go from hydrogen, which just has one energy level, to lithium, which has two, to sodium, which has three, to potassium, which has four, and so on, every time you drop down, you're adding an entire energy level where the electrons can go. So that's going to take up more space. So it makes complete sense here. As you go down, you would expect the atoms to get bigger because they have an entire extra energy level, which is going to take up more space. So as you go down any column on the periodic table, the atomic radius or the atomic size gets bigger because there's more energy levels. And it comes back to one of those three reasons. This would be like factor number one, if you remember from that slide. As you go across any row, though, left to right, the atoms get smaller. It makes sense here. As you go across any row, you're in the same energy level. So you're not going to add size because you're not adding energy levels as you go across left to right. But what's happening is you're adding a proton to the same energy level as you go across from one element to the next. So essentially what happens is your nuclear charge is getting stronger. Your nuclear charge is getting greater, or your nucleus is getting stronger, and it's pulling in those outer electrons more, so it makes the atom itself smaller. You really need to think about this here. If we look at the third period or the third row on the periodic table from sodium all the way across here to argon, you can see here from this picture, the size of the atom gets smaller. You're in the entire third row, so you're not adding energy levels here. So it's not going to get bigger. But what happens is, as you go from sodium to magnesium to aluminum and so on, you're adding a proton every single time. So what's happening is your nucleus is getting stronger every time you add a proton, and your positive nucleus is pulling in the outer electrons, pulling in those negatives even greater every time you add a proton. So your nucleus is getting stronger, which pulls in the electrons, which makes the size of the atom smaller as you go across. So this would be like factor number 2 on that list. The effective nuclear charge gets greater as you add electrons going across left to right. So the size of the atom gets smaller. If I ask you, why does it get smaller as you go across left to right? You can't say because it decreases. You have to explain this in terms of the nuclear charge getting greater. So this picture just shows what we talked about here. As you go down, the size of the atoms get bigger, and as you go across, the size of the atoms gets smaller. So in theory, the biggest element you would expect to be on the bottom left, and the smallest element you would expect to be on the top right. Now we're ready to talk about our second big trend here, and you're going to see this one has some similarities, but it's the same idea. You need to know what it means. You need to know what the trend is as you go down and across, and then you need to know the why here. It's best to group these together. So ionic radius here is going to be very similar to atomic radius. So if you know atomic radius and you study that one really well, ionic radius has basically some similarities and a few slight things that are different, but it makes your studying a little bit easier here if you kind of group it together. So ionic radius is going to be half the distance again, but this time between two ions. So now we have charges here. So it's exactly the same as atomic radius, all right, except that we're putting two ions of the same element side by side, measuring half the distance between the two nuclei. So it's going to follow the exact same trend in terms of as you go down, it's going to get bigger, and as you go across, it's going to get smaller. But there's a slight difference here, all right? Cations are always going to be smaller than the original non-charged atom, all right? So positives are always going to be smaller than the original neutral atom of itself, and anions are always bigger than the original neutral atom of itself. So we'll talk about why as we go through this, but some people get a little confused by this picture, so I just want to point this out here. In gray, they're showing you the normal atom. So this would be like normal atomic radius, normal atomic size. So that's what's in gray for all of these. As you go down, they increase. You go across, they decrease. But then the colors are showing you the cations and the anions here. So charges. So notice in red here, this is a lithium plus, and then we have sodium plus, and so on. As you go down, they still increase. You go across, they still decrease. But notice the red or the pink here for the lithium 1 plus is smaller than the original lithium that doesn't have a charge. That's what we expect. Cations or positives are always smaller than their original atom. And then notice for the anions here, which are in blue, they're always bigger than the original gray or non-charged atom of itself. All right, so that's something to pay attention to. Very similar to atomic radius, but there are some slight differences here. So definitely know the definition, know the trend, and then we need to talk about the why here. The good news for the Y as you go down for ionic radius is that it's exactly the same as atomic size. As you go down, you're adding more energy levels, therefore the size of the atom must be bigger. So this is very similar, exactly the same. You can make this very easy when you're studying. Just kind of, if you know atomic radius, you know the Y here for ionic radius as you go down. There's more energy levels. It'd be like factor number 1 if you reference back to that first slide where we talked about all the different factors. As you go across left to right, the size here we said is going to decrease. And the basic gist here is the reason this happens is because, again, the nuclear charge gets greater. As you go across left to right, you have more protons in the same energy level. So your nuclear charge becomes greater and it pulls in those outer electrons more, making the atom itself smaller. We just need to remember here that cations and anions are different. So this is kind of a difference between atomic size here. We said cations are always smaller than the original no charged atom. And it makes sense because if you're a cation, you're positive, you lost electrons. So think about that. If you lose electrons, your nuclear charge is essentially even greater. All right, the strength of your nucleus is even greater because now you lost negatives. So it makes sense that the nucleus pulls the atom in even tighter and makes the size of the atom smaller. And then the reverse is true for anions. Think about what happens in an anion. For an anion, anions gain electrons. So essentially, you're adding in negative charges, so it dilutes the nuclear charge and it basically makes it weaker and the size of the atom gets bigger. Okay, so you really need to think about that. The cations are always going to be smaller because as they lose electrons, the nuclear charge gets greater and makes everything pull in tighter and get smaller. Whereas anions, as they add electrons, dilute the nuclear charge and the atom itself gets larger. All right, so definitely know this difference for ionic radius compared to atomic size, but otherwise it's very similar here to atomic size. Again, you can just see this picture here showing this. In this case, the green are the original no charged neutral atoms here. So this would be like atomic size. You go down, you increase. You go across, you decrease for the green. And then in blue, they're showing you the cations. Same deal. As you go down, they increase. As you go across, they decrease. But remember, the cations are always smaller than the original no charged atom. So the blue here are always smaller than the green. And over here, the red are your anions, and the anions are always bigger than your original no charge atom. You need to know the whys here, and you need to know the trend and the definition for ionic radius, just like you do for all these big trends. The third big trend we're going to talk about is ionization energy. All right, this is where we start to see kind of a switch in the trends. If you remember atomic radius, atomic size here, and you get that all studied and know that ionic size, ionic radius is pretty much the exact same thing with some slight differences, you just need to remember the last three big trends are going to reverse here in terms of the increase or decrease going down and across. So ionization energy, again, first thing you need to know is the definition. If you don't know what this means, you can't fully think about what's going on here. So ionization energy is the amount of energy you need to remove a valence electron. So if you walked up to an atom and you wanted to steal away a valence electron, how much energy would you need? That's the ionization energy. How much energy does it take to pull away an electron? All right, so definitely know the definition first. And then the trend is going to be reversed atomic and ionic size here. As you go down, we decrease. And as you go across, it increases. And that's what you're going to see here for the last three here for ionization energy and the other two remaining. It's going to decrease down, increase across. So it's reversed of atomic and ionic. And we need to know why this happens. As you go down any column, why does the ionization energy decrease? Basically, why does it get easier to remove an electron? Think about this. If ionization energy is the amount of energy required to remove an electron, and as you go down, it gets lower, that means it's easier to steal as you go down. All right, well, think about it. As you go down any column, all right, you're adding more energy levels, which also means that there's more shielding. So if you look at factor number 3, more shielding as you add more energy levels, which means it's a little bit easier to pull away that outer electron because those inner energy level electrons are feeling the full pull of the nucleus. All right, so as you go down any column, you're adding more energy levels, which means there's more shielding, which makes it a little bit easier to steal away an electron, so it decreases. So this would be relating to factor number 3 if you think back to that first slide. So again, you need to know what ionization energy means to fully understand why this is happening. As you go across left to right, any row, any period here, the nuclear charge is going to get greater. Therefore, the ionization energy is going to increase. So you really need to think about this here. Left to right, as you go across from one element to the next, we already talked about this for atomic size. As you add protons to the same energy level, your nuclear charge is getting greater. So it makes sense that if your nucleus is stronger, as you go across from one element to the next, it makes sense that it's pulling in those outer electrons more. It's holding on to them tighter. So if you want to remove an electron from an atom as you go across, it's going to take more energy here. So understanding what ionization energy means really ties in with this. As you go across, the nuclear charge gets greater, so it takes more energy to pull away an electron. This would tie in with factor number 2 back on that original slide. There are some exceptions to this. If you look at this table here, you can see that we said as you go across any row, it should increase in terms of ionization energy. But if you notice, look what happens here. As you go from beryllium to boron, that's going across the table. It should go up, but it actually drops. It goes from 899 to 801. And then same thing from nitrogen to oxygen. It should go up because you're going left to right. It goes from 1402 down to 1314. So you need to think about this a little bit. We're going to keep it easy here for you and basically just say the reason why these little blips or these little exceptions occur is due to stability. All right. For example, boron is a little bit more stable, doesn't or wants to give up its electrons a little bit more compared to beryllium, so it's a little bit lower. Same thing for nitrogen, oxygen. Oxygen wants to give up its electrons a little bit more, so it's a little bit lower there, even though there are blips here. So for this, if this says like why do these exceptions occur, you can just say let's due to stability, knowing that there's a more of an AP explanation going on here, but for our purposes, you can just say stability. And you need to understand that there are actually blips to these trends all over the place, and we're just trying to memorize a general trend here. We're not going to study and memorize every single little exception, but generally here, as you're looking at these trends, they do, increase or decrease as you go across with some slight exceptions. And something else I want to point out here, if you notice, anytime you want to remove a second electron, we call this the second ionization energy. It always takes more energy. It always gets harder to steal. So we always say that ionization energy increases with every electron you're going to remove. So even if you look here on the periodic table, so beryllium, first electron you want to remove, it's about 899 kilojoules per mole. But then when you go to take the second electron away, it goes up to 1757 kilojoules per mole. And then if you try to take a third, it goes up to over 14,000. So every time you try to take away an electron, it takes more and more energy. And that's something you should understand here. This picture is just showing you this idea of ionization energy. So in blue here, you have the noble gases. So we said as you go down any column, it should decrease. And notice the general trend here is it gets lower as you go down the noble gases. We also said as you go across left to right, any row, it's going to increase. So for example, here's lithium across the neon, it goes up. Sodium across the argon, it goes up. All right. There are some slight blips, but for the most part, it follows these trends. So again, you need to know what it means, know what happens as you go down and across in terms of increase or decrease, and then you need to know the why. Just saying it increases or decreases down or across is not explaining the why here. You really need to make sure you understand why this is happening. Our fourth big trend that we're going to look at is electronegativity. Again, the definition is important if you want to be able to fully explain and understand what's happening here. So electronegativity is an ability of an atom to attract electrons toward itself when it's in a compound. So you're talking about electronegativity, you're talking about an atom's ability to attract those electrons, bring the electrons toward itself. All right. So it's just like ionization energy in terms of it decreases down and increases across. So as you're studying these trends, try to keep some of these things together here to make it easier. Remember, ionization energy, electronegativity, they'll follow the exact same trend, but there'll be different definitions, obviously. Electronegativity is your ability to attract electrons toward yourself. It decreases down, increases going across here. And I really like this picture because it does show you this, especially over here in the nonmetals. As you go down, you can see the general trend is it decreases. And as you go across, you can see it gets much greater. And if you look over here, fluorine is off the charts in terms of electronegativity. All right. Typically, fluorine is like the most electronegative element on the planet. So there's a little kind of pickup line you can use here. You could say that I'm attracted to you the way fluorine's attracted to electrons. It really does work. And typically, all these elements over here near fluorine, those are the ones that are going to be very electronegative as well. So after fluorine, you have oxygen, nitrogen, chlorine's very electronegative as well. So if you want to talk about in terms of greatest electronegativity, you're thinking about fluorine and the elements closest to him. So the ability to attract electrons toward yourself is electronegativity. So as you go down any group, why does it decrease? Why does the ability to attract electrons get less? Well, think about it. It has to do with more energy levels, more shielding. As you go down, you're adding energy levels, you're adding more and more shielding. The nucleus has all these other electrons that it's attracted to. It really doesn't want to attract more electrons, or it can't attract more electrons as much. So this would be tying in with like factors 1 and 3. If there's more energy levels and there's more shielding, the nucleus really can't attract more electrons, so the electronegativity is going to go down. But then as you go across any row left to right, the nuclear charge is going to get greater. So if your nuclear charge is increasing, your nucleus is getting stronger, it's going to have a greater ability to attract those negatively charged electrons. Think about if your nuclear charge, which is positive, is greater as you go across any row, it would make sense that it's going to attract those negative electrons even more. So the electronegativity is going to go up. All right, so this would be like factor number 2. The effective nuclear charge is getting greater as you go across any row, so you can attract electrons even more. Again, you can see over here in this color coding, you can see fluorine's off the charts, and usually those elements that are very close to fluorine are going to be very electronegative as well. The last of the big trends here is electron affinity. Again, knowing the definition is going to be very important. So electron affinity is the amount of energy that's given off when an electron is added. So basically, if you gave an atom an electron, how much energy would they give in return? Okay, so it's going to follow the exact same trend as ionization energy and electronegativity. It's going to decrease down and increase going across. Basically, as you go down, you're going to get less energy given off. And as you go across, left to right, more energy is going to be given off. So in terms of the why this happens, you just need to think about it in terms of electronegativity. So like I said, group these things together as you're studying. It makes your studying a little bit easier here. But if you think about it in terms of electronegativity, all right, if an electron, if an atom wants an electron, remember as you go across left to right, the nuclear charge is getting greater, so they want electrons, they're going to give you a lot of energy here. Okay, so the amount of energy that is going to be released if they want an electron is going to be greater. So as you go across, that's what happens. But as you go down, their electronegativity decreases. They don't really want the electrons. They can't attract those electrons toward themselves as much. So they're not going to give off that much energy. All right. The idea is think about like if you had two people, one loves donuts and one doesn't. If I were to bring in, 2 boxes of donuts for the person who doesn't like donuts, they're not going to really give me any money for them. But if I brought in 2 boxes of donuts for a person who loves donuts, they're probably going to throw their entire wallet at me. All right, it's the same idea here. If an atom wants electrons, and as you go across, this is what happens, you're going to get a lot of energy being released. As you go down, the atoms don't want the electrons. They can't attract the electrons toward themselves as much. You're not going to get as much energy. So for these big 5 trends we looked at, you definitely need to know the definitions, know what happens as you go down and across, and then know the why for all of them. Because these are the big trends, and we're going to look at some smaller trends here as we go. Now that we're done with the bigger trends, I do want to look at some smaller ones here. So we're going to talk about metallic character and reactivity. As you go down the metals, the metallic character and reactivity are going to increase. So people will say, well, what do you mean by metallic character? It basically just means like how the elements are going to act like a metal. So as you go down the metals, you would expect them to act more and more like a metal. All right, so that's what we mean by metallic character increases as you go down the metals, but the reactivity of the metals also increases as you go down. So if you look here, we talked about the alkali metals in the far left column of the periodic table being very reactive with water. So this picture shows you lithium, sodium, and potassium reacting with water here. Well, as you go down from lithium to sodium to potassium, according to the trend, they should get more reactive. And that's exactly what you see happening here in the picture. Lithium kind of fizzles with water. You can see sodium kind of sparks a little bit, and then potassium is like completely catching fire. So that's definitely shows this trend. As you go down the metals, you should see the reactivity increase here. But then this is reversed for the halogens, all right, for the nonmetals here. So when we talk about this in terms of nonmetals, we only really look at the halogens, so fluorine on down. They're reversed. As you go down the halogens, the reactivity decreases. So fluorine is the most reactive halogen, and then as you go down to iodine, that would be the least reactive halogen. So this is just something you need to study and know. As you go down the metals, they get more reactive, but then it's reversed for the nonmetals, for the halogens. As you go down, they decrease in reactivity. Knowing the definitions, knowing the trends, knowing the why is important, but you also need to be able to take this information and apply it to different elements. So as you can see here, these questions are going to give you a chance to practice this. You have to think about what's going on with each of the trends, and then you have to analyze the choices and pick the one that fits here. So what I would do is I would get out my periodic table. I would use notes here and think about what these things mean and try to answer all of these questions. And then when you resume the video here, we can go through these and see how you did. So pause the video right now. Let's walk through these and see how we did here. So the first one says, which has the greater atomic size, phosphorus or chlorine? So if you notice, phosphorus and chlorine are both in the same row. All right, and the trend for atomic size is as you go across left to right, it decreases. So chlorine is further to the right, so you would expect it to be smaller. All right, has a greater nuclear charge, so it's pulling in those outer electrons more. So chlorine is going to be smaller, so phosphorus would be bigger or greater in terms of atomic size. When we look at the second one, lower ionization energy. Ionization energy is the amount of energy required to remove an electron. So if you're a lower ionization energy, basically which of these is easier to steal from? So strontium and barium are in the same column here. Barium is further down. If you remember, the more energy levels, the more shielding you have here, the easier it is to remove an electron. So barium is further down. So he's going to be easier to steal from, a lower ionization energy. Which of these has a higher electronegativity? So remember, as you go across, you're going to increase in terms of electronegativity, and as you go down, you're going to decrease. Well, oxygen and sulfur are right in the same column. Sulfur is a little bit down, it's right below it. So as you go down, it's going to decrease. So oxygen is going to have a greater ability to attract electrons here. The next one says, which has less shielding? So we didn't talk about this explicitly. We just said that you need to think about this in terms of energy levels. If you have more energy levels, you have more shielding. So if you have less energy levels, you would have less shielding. So lithium is in the second row, all right, versus potassium, which is in the fourth row. Potassium would have more energy levels and more shielding. So lithium is the smallest. And then it says for the last one, which of these is more reactive, iodine or bromine? So now you have to remember here that this is the nonmetals. As you go down the nonmetals, all right, the reactivity decreases. So bromine would be more reactive because it's closer to the top. So you definitely need to be able to take these trends and think about them and be able to answer questions about them as well. We talked about the big trends, and I just want to talk about some of these minor trends here before we're done. We did kind of mention this, but we said that for shielding, all right, the more energy levels you have, the more shielding that there is. So as you go down the periodic table, your shielding always increases as you go down. All right, if you have more energy levels as you go down the periodic table, you would expect more shielding. But as you go across, all right, you're in the same energy level. You don't change energy levels as you go across any row. So the shielding is constant as you go across. If you need more energy levels to have more shielding, if you're not adding energy levels, you're not going to have any more or less shielding as you go across. So notice if you ever answer an across question and try to explain it with shielding, you know you're wrong, because the only time you can talk about shielding is when you're going down a column. All right, so we never talk about shielding going across. We said that nuclear charge is essentially talking about the strength of your nucleus. So notice we said for a lot of these trends, as you go across, the nuclear charge always increases. You're in the same energy level as you go across, and you're adding more protons as you go from one element to the next. So as you add protons to the same energy level, your nuclear charge gets greater. We never talk about nuclear charge going up and down. So if you go back and look at your notes, anytime we talked about going down, we never mentioned nuclear charge. Nuclear charge was always the explanation as we went across. So that's something very important to remember. As you go across, the nuclear charge always increases, and then you can think about how that would affect those bigger trends. We said in the notes, the metallic character always increases as you go down the metals. So basically, this is saying like, uh, how they act like metals. They basically act more and more metallic as you go down. And then we didn't talk about it explicitly going across, but it kind of makes sense. On the left side of the periodic table are your metals. On the right side are your non-metals. So as you go across from the metals to the non-metals, it makes sense that the metallic character is going to decrease because you're no longer a metal. So this is just a nice summary of metallic character. And the last minor trend here, reactivity, we did mention, but I just want to reiterate this. As you go down the metals, the reactivity always increases. All right, so as you go down any column of metals, you get more and more reactive. But for the halogens here, the fluorine group, we only really care about them for the nonmetals. As you go down the halogens, they always decrease in reactivity. So you have a good idea here of the major trends on the periodic table and even some of the minor ones. This definitely requires thinking and studying here in order to be able to fully grasp this.